rivals in ASCE that meet and they get together and they have a lunch and they invite us students. So it's great for us to be able to go and interact with them and get food with them. Sign up is on the blog for the luncheon, so go to our blog. It's byuasce.blogspot.com. Yes? Oh, and the first 9 students to sign up will be able to go for free. So a major perk. The blog is byuasce.blogspot.com. Okay, senior leadership and networking points. So this is really important. We need you seniors to help out, but not only that, you guys need us, because you guys get a point for seminar if you do a senior leadership point or a networking point. So if you don't do it, you're going to get -1 in the class, and that ends up being an A-. So you don't want to get an A- in seminar. So come to us. You need to get a leadership point, you have to plan, organize, write a summary, take pictures, email all that to our email. But most of all, you have to attend the activity to get to the point. And then to get credit, you need to just come talk to one of us and we'll put you on a project. Or if you have one of your own ideas, that works too. So we're having a networking dinner in the beginning of December. That's up next on our list. So if you want to take charge of that, come talk to one of us after the meeting or email us, even better. So we have an awesome activity coming up, and I'm really excited about this. I hear YouTube is going to be there. It's October 26th, so next Thursday at 5 p.m. Location will be announced at a later time. We're still trying to reserve a room. There will be pie and root beer. And if you want, you can submit your favorite YouTube video to the link on the following form on the blog. And what it's going to be an hour-long film festival of all of our favorite funny and inspiring and hilarious YouTube videos. So please RSVP so that we know how much pie and root beer to get. Alright, also next Thursday, so this is our 3rd and 4th activity that's going on next Thursday. We have 2 field trips. The first one is at 12:30 p.m. We'll be visiting the hydroelectric power plant at the mouth of Provo Canyon. And in case that doesn't work for you, we have a tour of the Orem City Water Reclamation Plant at 3 the same day. So Ben Nelson is in charge of that. Yeah, go Ben. Sign-ups are on the blog, and they're going to be awesome field trips, so please go. All right, and then stadium cleanup. There are 2 of them. It's kind of a funny picture, but it's very true. You get a hold of fire hose if you do stadium cleanup. There are 2 left. One is versus San Jose State, it's right after the game, and then the other one is University of Massachusetts on November 18th. And luckily both of those are afternoon games, so you won't be up until 3 a.m. doing stadium cleanup. You'll only be there till it's getting dark. And if you come to 2 stadium cleanups, you get your registration for Rocky Mountain Conference paid for, which is a huge perk. It saves you a lot of money. So if you're with Steel Bridge or Concrete Canoe, it's really worth it to go. If you haven't been to any, go to these last 2. And then if you're not in either of those teams, still come. It's a great way to get your service points knocked out all in one go. 2 more activities for service is Habitat for Humanity on November 4th and December 2nd. We still need people to sign up for December 2nd, so please see the blog or Facebook to sign up there. And then we need a senior to be in charge for each day. Once again, this is a way for you seniors to get your leadership point. So please email us at byuasce@gmail.com if you want to take charge. So today we have a great presentation, or 2 presentations I guess, from Dr. Gordon and Dr. Scott, 2 of the great minds in our civil engineering professor staff. Dr. Borden, so this is his biography. He is an assistant professor in the Department of Civil Engineering at BYU. He began his career at BYU where he earned his both bachelor's and master's in civil engineering, and then he worked as a member of the technical staff at Sandia National Laboratories, where he developed computational geometry methods to support Sandia's finite element codes. After 5 years at Sandia, Mike went on to earn a PhD in computational science, engineering, and mathematics from the University of Texas at Austin. From 2014 to 2017, he was a faculty member in the Department of Civil Construction and Environmental Engineering at NC State. Mike joined the faculty at BYU this year in 2017. Okay, and then after Dr. Borden, we'll have Dr. Scott. I'll introduce him now so that he doesn't have to do so much introduction when he gets up. He received his PhD from the University of Texas at Austin, which is the same school Dr. Borden went to back in 2011, and he's been at BYU since 2012. So first, let's hear from Dr. Borden.
Okay, well, thank you for that introduction, for greetings to you all. I'm happy to be here today. So, well, what am I going to talk about today? So I do my work when I'm outside of the classroom. I do work with computational mechanics, is going to be able to do. And you see this thing here about mathematics. What's up with mathematics in an engineering seminar or an engineering graduate? So I remember when I was here as a student, there was a college-wide seminar. It was over here in the Joseph Smith building. And the person talking, I think, was an executive at the time. He's the BYU alumni, an executive at Intel or IBM or one of these tech companies. And he got up, and the first thing he said was, since I graduated, I have not solved PDE, or partial differential equation. I don't know, some of you may know what that means, some of you may not. And people applauded, and I was kind of probably clapping too at the time in my ignorance. Right, so here we are, engineers, we don't do math, we do engineering. Well, I'm going to tell you today, and I'm going to argue that not only do you do math, but he did math too, and you solve very difficult PDEs in your life. So, how many of you play basketball? You play basketball, how many of you do ultimate frisbee, or something where you're throwing the ball or an object, you get angry at the dog chasing you down the sidewalk. How many of you have just thrown something through the air, right, at something, it came close to what you were thinking? But when you did that, you were solving a system of partial differential equations. Not only were you solving partial differential equations, you're solving these equations. They're called the Navier-Stokes equations. These are very difficult equations to solve. You try to do it mathematically, but you're doing it every day as you're throwing something, walking through the air. These are the equations that govern something moving through a fluid. For example, basketball here, or your frisbee, or your rock, whatever you're throwing at that dog that's bothering you. But how do you do it? Right? You do it intuitively. Right? We develop intuition to solve difficult mathematical equations just from the way we live our lives. But the problem with intuition, and the reason we need mathematics, intuition doesn't scale. Right? We can learn how to throw a ball, but it's not very easy to scale that throwing the ball up to a spacecraft re-entering the Earth's atmosphere. But there's way too much going on beyond our everyday life to be able to solve this intuitively. And you say, okay, well, we don't do spacecraft, we're engineers, right? We're either designing structures or what else you do, wastewater treatment plants or highways. We don't do this. Well, right, we do engineering intuitively. Someone has a little ditch going across, they nail some boards together, they throw it across the ditch. So we can do engineering by intuition, but again, intuition doesn't scale. Right? And you can't just say, okay, I built a bridge. You say, well, okay, hopefully you've seen this before and know what this is, the Tacoma Narrows Bridge. If you haven't seen it, look it up. The excitement happens after this, but class. But, where does intuition involve? A lot of engineering went into this design of this bridge. But if you think back to some of the first suspension bridges, for example, the Brooklyn Bridge was really one of the first big suspension bridges that we built. And if you haven't read about this, I suggest you do. There's one book I read that we're going to recall, but very interesting. very informative about engineering. There was a lot of work, and this thing is massive, it's huge. Right? These columns are enormous, they're heavy, they're big, and it was a success. They're still standing. People took this design and said, okay, well, can we make it lighter? Can we make it smaller? Can we make things slender? And using experience from the past, they make it smaller and smaller until they got to a point where they got they went too far. And they designed a bridge that wasn't able to operate in the environment that was given. Right? So, what do we say? Intuition doesn't always work. You say it's engineering, but it's also there's some intuition. Well, so we can use mathematics and computers to help guide our engineering intuition. And this is the type of work that I do outside of the classroom. So we need to develop mathematical models of the world around us. And we need some way of using those models on the computer. So let's just ask the question, what is a mathematical model? So here's a very simple example of a mathematical model. This is kind of sort of beginning the work that I do. So here's a truss member. A lot of you hopefully have seen truss members, maybe some of the freshmen, I don't know, but they look at these in 103 statics, you start looking at truss members, right? We say, okay, what does a truss member do? Well, we put a force on it and it changes its length. Okay, well, what's the relationship between that force and the change in length? Well, we can develop a mathematical model that tells us. This is a very simple mathematical model. So now we have an equation there, bottom right, my right, your left, bottom left corner. But we've made some assumptions. So mathematical models, you say, okay, we're going to describe the behavior of something, but we have to make some assumptions. The world is too complex. Otherwise, if we don't make assumptions, we end up with those first equations that I showed. To solve. So this we can solve with just by hand. But these models can become much more complex and model things that are way more complex than a truss member. So here's a computational prediction, you could say. It's a computational simulation. I'm going to show there's going to be an animation. This is, I don't know, there's not much simulation. But this is a crush test. So this is think of a rectangular tube that's going to be crushed from the top. So you think about it, you can stand on a soda can and it crushes. This is what happens. So we say, okay, can we model it? Oh, went too far. Sorry, there we go. So we start crushing this thing. So a computer can now predict what will happen when we crush it. Now this mathematical model has a lot more going on than a simple truss member. Right, we no longer are assuming that things are kind of changing small, the deformation. We're not assuming anymore that the material stays elastic. You know, there's a lot of plastic deformation going on. There's contact between surfaces, but all of this is described mathematically first before we can do anything computationally. Okay, so let's get more details into the type of work that I do. Okay, so my work, I try to develop computational tools that help us predict material behavior under extreme loads, I guess you could say. When materials start to fail or fracture. So here's, real world application. Look, I go out and find pictures on the internet. That's how I experience the world often. I do other things outside. Anyway, so we have the top left picture there is that's what happens when a ship hits a contact mine in the water. And so that's a Navy ship. This was back in the early 90s in the first war in Iran, I believe, or Iraq, when this ship was one of the ships that hit. It was USS Tripoli, I believe. All right, so what happens? Well, you hit a contact mine, you get all this, there's a large deformation, a lot of things going on in that material. It's kind of beyond just our basic truss member. The one there on the upper right, that's what happens when a projectile hits the armor plate. And then this one here on the bottom, a lot of you have probably experienced this yourself. Right? You drop your phone and things break and you're sad. If you're my wife, you get a piece of tape and try to put it over the top and hold the books together. Eventually, you have to get a new phone. Right? It doesn't work very well. So, okay, so we want to develop computational models to predict what will happen in these these circumstances. So what do we do? So what are the steps developing computational models? Well, the first thing, you have to have some kind of a mathematical description of whatever it is you want to model. You can start with those first equations I showed. Those can be simplified. Most of this work in the mathematical area has been done. And interestingly enough, you look back in kind of the development of these models or these descriptions in mathematics or the mathematics that we use as engineers, a lot of it was done by civil engineers. So there's a heritage of mathematics and civil engineering. So we develop these mathematical descriptions. Then we have to do some additional approximations and simplifications so that we can do something with them on the computer. So this is where, as an engineer, or in my work, I understand the mathematics enough that then I can say, okay, we can simplify things in such and such a way so that we can solve it using a computer tools we have. And then there's these numerical and computational tools, the different ways of describing the model that we've developed in the computer that help us to improve the results or predictions. And then, of course, you can say, okay, well, I've got this model that makes these nice, I'll show that picture of the crush test, makes a nice picture. Does it mean anything? Well, we have to compare the results from our model to really what happens in the world. And say, okay, these give us some results that we can trust in certain situations. So, let me give you some details. Okay, now here's some math. Most of you won't understand this. I didn't understand it for a long time. But this is a mathematical description of what happens in a brittle material during what's called quasi-static fracture. Right? You say, okay, well, there's a lot going on there. All that is saying is that this equation up at the top there is an energy equation. If you think about stretching that bar, the truss member, when you stretch it and hold it, it stores energy. You can release it, and then it will release the energy. So there's what's called elastic energy. That's kind of that first term up there. And then there's an energy that is in describing fracture. You say there's a surface energy. What is the energy it takes to create new surface area in a material? That's what that equation is telling us. It's telling us that there's a contribution of the energy from just the elastic energy in a material and contribution from what energy has been required to create new fracture surfaces. And this is a good theory under the assumptions that have been made developing this theory. The problem is it's very difficult to compute an answer with that theory, right, with that equation. There are things going on there that I don't want to get into, but usually put you all to sleep. You're not asleep already. But you can't really compute an answer with that equation. So you have to do something with it. And here's another, probably looks mostly like a foreign language, and mathematics often is until you can learn it. But these are some simplifications. Okay, now that doesn't look any simpler. It looks more complex, right? But there's been some changes made. We've replaced some things that are happening over an unknown surface to some things that are happening inside the volume of that body, whatever's going on. So we make some approximations, things that's not an exact representation of the first equation, but under certain circumstances, if you know the mathematics, which is actually beyond kind of my experience, you can show that that second equation there, that approximation, will give you the same answer as the initial equation. Right? Or the answers will converge, as they say. That means you look at close enough that you can trust the answer that you have that you got there. And here's kind of a figure of what's going on. I don't know if this figure makes much sense. So think of that bar, that truss that I had before. If you pull the bar far enough of a force on it, eventually that bar will crack. Right, you'll get a fracture. Maybe some of you have seen this in your, I don't know the numbers of the classes here. You do one class, we do these, is it 3 or 4? Okay, 3 or 4. Right, you pull these little metal things apart and neck and fracture. Well, think of that blue line. When it equals to 1, there's no crack. When it equals 0, that's what the crack is. Right? So think of your bar on the x-axis. And you have a nice clean crack. That's what happens in the world. Well, this approximation says, okay, approximation is the red line. It says, that crack is there, but we're going to kind of approximate it. Instead of as a sharp step, which is very hard to do computationally, and approximate it as something that comes in gradually. right, to that 0. And that's kind of what this approximation is doing. It's approximating a step with something that is kind of a little nicer to handle computationally. Now, that's the initial model. How many of you, does anybody here, I know sometimes seniors do, anybody here that is taking a finite element class from Dr. Scott? Nobody? Okay, well, so in there I've heard, he teaches right next to me, and I've heard him talk about strong form and weak form. Anytime people talk about finite elements, I'm kind of paying attention in the background. It's kind of what I do. So anyway, from that theory, that equation, we can do some manipulations, and we get another set of equations that are called governing equations. And these are the equations that we say govern the motion or the response of a body. So there's two equations there. Again, right, we solve some of these equations, not the first one, linear momentum, that is again, you're seeing this if you're rolling, if you're throwing that ball, if you say we're throwing the ball in a vacuum, we never throw a ball in a vacuum. That's what we do. As engineers, we simplify things. If you throw a ball in a vacuum, then you're governed by this linear momentum. The Navier-Stokes equations simplify. So, anyway, we have some equations there. Those are the equations that we're solving on the computer. So, what happens? What does it look like? All right, some people probably get up here and show like structure or, I don't know what people, I haven't been in here for 15 years. It's been too long. Anyway, so I just show you, animations of things. This is what the results from a computer will look like. So imagine taking a specimen. So that's what we're drawing here. Think of this as a little rectangle, maybe a piece of metal. And we've taken it and we've cut where that line kind of goes through the part there, or the domain. We've made a little crack, or a little cut. So we have what we call an initial crack. And we're going to model this using these equations that I have shown before. So here is what it would look like initially from the computer. The top part shows what we call the, it's just a scalar field that describes the location of where that crack is. So red is where there's a crack, blue is where there's no crack. The bottom here is just going to show some stress waves. Both of these will go at the same time. You'll kind of see some things moving, but this is what it looks like. So we load this thing up, traction on top and bottom, stress, pull it apart on top and bottom. We get these cracks that form and they start to branch and you get these other things. So there you can see that's kind of an idea of what this computational model does for us. So it shows us what would happen if we were to load this part in some kind of tension load there. And the nice thing is that this is all done on a computer code that somebody who was trained as an engineer, me, wrote themselves. So all of you have the background now to make a simple little picture. What I call, sometimes I tell people my research is just generating videos. But there's more to it back there. Anyway. Okay, so that's a pretty simple case. But what about now real world? And that was just a picture. Let's talk about these models. So here again, we're back to this ship that was damaged by a contact mine. And what do we do when we develop models? Well, like I said, we have to compare them to something. And so these were some experiments that were done not by me, but by another person in another university, where they said, okay, we're going to try to replicate or at least get some idea of what's happening in this ship when it hits a mine. So that what they do is they take the test plate. This is a steel plate. It's about an inch thick, I think, about a meter in diameter. They bolt these things to what they call a reaction frame. It's just a big steel frame. And they lower this into the water, and they detonate a charge in front of it. And what happens is, you can see there on the right, what the result of loading this thing. Okay, so well that's great. You can do this in the real world. Can we simulate this computationally? And our tools that we have at least get somewhat close to what's going on here. So we develop, there's some words on there that probably don't mean a lot, but we just create a geometric representation of this plate in the computer, so we have to develop some kind of computational model or description of the plate, and then we run this through our code. So here you can see there's already kind of some initial cracks that are set on that plate, and we simulate the detonation of that load, and you see, okay, well here's what happens. This is what happens computationally. These are the results that we see from our computer code. There's plots there just showing the deformation. So we get this thing. Okay, it's starting to look. It looks similar to what we got. from the real world. And you can come back and make some closer details. So there again is experimental results. You start to get some detail. You can't see it very well, but where those bolts are, you get little folds. They'll show up in our computational model. And you start to get, you get a similar, it's not exact. Right? We're not doing the exact model. We've made some assumptions against simplifications. But we get very close. And people in the computational world say, yeah, that's a very good result. We're starting to get predictions. Okay. So let me just wrap it up here. Just leave time for Dr. Scott. So the idea is that we want to be able to use, what am I doing? I'm trying to develop tools that engineers can use to guide their intuition, to predict, right? Computation, predicting what will happen to a given set of loads to the structures. Now I work kind of in fracture. Hopefully if you're designing buildings, you're not analyzing anything where it's going to collapse. You're kind of far away from that. Anyway, and then the thing that I like about this is I sat here several years ago as an engineering student, at the time planning to become a structural engineer. And I had some experiences here that kind of introduced me to this computational world, and it changed the direction of my career plan. But because of the foundations that I had as a civil engineer, that wasn't too difficult to make that transition. So you guys are in a very good place to be here. You've got plans of where you're going. If things change, you have, as a civil engineer, you have the training to solve problems, foundation to kind of make career choices that are direction changes as they come up. So you're in a good place. Anyway, that's my presentation. So thank you for your time.
Dr. Scott.
I recognize a lot of you. How many of you are in my class right now? Yeah, about a quarter of you. How many of you have been in classes with me in the past? How many of you have been in class with me, period? Just either, so about half of you. Okay, similar kind of a setting, huh? Big auditorium, you guys listen to me talk. Those of you who are in my class, this is 3 days. I did it yesterday, today, and then tomorrow we'll meet again. So let's see, let's get this thing working. Okay, so I am going to they told me to try and introduce you to what I do in my research. So that's what I'm going to try and do. How many of you are seniors? How many of you are, so is it like, how many of you are juniors? So it's like pretty equally distributed, okay. So, okay. How many of you have ever heard of engineering design? Okay, who could tell me what that is? We have an eager student here who wants to tell me what that is. What is engineering design?
It's when you figure out what the requirements are and build something.
Okay, great. So you have some idea of what you want to build. You generally take an educated guess about what the important parameters might be that govern the design. And then you just run off and build it? Okay, then you do some analysis, it's called. So engineering analysis is part of the process. Engineering analysis will tell you something. What do you think it tells you? What's the purpose of doing the analysis? Right. So you've guessed, really. At least you have some intuition hopefully guiding you, but you've guessed at some parameters. It will tell you whether your initial guess is good or whether there's some refinement to that guess that could be made, and you make it, and that generates a new design. Then you do another analysis, and so it's an iterative process. So you guys are first, at least for from what I understand, the first place that you really see very simple engineering design is in 203, where you'll take we teach you some very simple analysis concepts, and then we might kind of rearrange the equations, and you'll use them in the design context to try and maybe come up with the cross-sectional area of a beam or something like that. Okay, well that's all well and good. How do you do this for like a full car? I mean, it's one thing to design a beam. It's another thing to design a spacecraft or an automobile or a warfighter. How does it work in that setting? Okay, beyond just kind of the traditional, simple structures that you might have been introduced to, how do we move beyond that? How does the engineering design process work? You guys, any of you seen it, been involved in it? Anybody? Or is this a question, a mysterious question? Anybody want to guess? Sure.
You start with the big object and work your way down to the details.
Okay, great. So the object is going to be big, it's going to be very sophisticated, and it's going to be detailed. So the first thing you have to figure out is, how on earth am I even going to represent it? How do you represent sophisticated designs? Like, let's say you have an automobile. Where do you put that design? How is it represented? Okay, a model is the right word. Where do the models go? If you go to Ford Motors, for example, as an entry-level engineer, and they want you to do some very simple design on some new automobile, what tools are you going to be introduced to? Anybody have any idea? Okay, CAD. I heard CAD. Okay, so designs generally, sophisticated designs are generally encapsulated in something we call CAD, computer-aided design. And it's just a digital representation of the design that maybe you have in your head. Okay, so we all know what CAD is. I'm sure you've used it. Isn't there a class on CAD in civil engineering? Okay. Depends on the application. Some of you are very demanding students, so you're constantly feeling like you're not getting the education that you need. That's okay. That's good. Okay, so what I want to talk about is that level of design. So I don't work on like things that we already know how to build. I work on things that have never been built before. That's where I live. So we don't always know even how to represent the object, how to move from design to analysis, and what the implications are. So that is my basic research area. Okay, so I only have a few minutes, so we'll just get through as much as I can. So here's the traditional process. So the top row there is what we would call the computer-aided design process, and then there's usually an associated or a partner kind of process called simulation, which is what Mike was talking about. So you'll have a concept, and then that design will be instantiated in some kind of a CAD package, some conceptual design package. There might be multiple packages through this process, depending on what level of design you're at. So you instantiate the design, you encode it in a computer, and then it begins to move from left to right, where eventually you want to manufacture the object. Okay? Well, you guys know that you can't just take a design and manufacture it. You should probably do some analysis to make sure that the design is feasible. So there's this kind of separate process that occurs where you get to CAD, and at that point, if you want to do simulation, you have to kind of generate a new model and then shove it into a new set of tools. Usually they're called finite element packages. Who's heard the word finite elements before? Oh, that's good. Yeah, about a quarter of you. So in the structural world, sophisticated structural design and analysis is done using finite elements, almost exclusively. If you kind of have more simplified things, there might be some simpler approaches that you can use. But I know, like, the first place that you see finite elements is actually in 321. You may not even have known it, but who's taken 321 already? Not very many of you. Is that true? Only like 10 of you have taken 321 in this whole auditorium?
There's like 60 of us in right now.
How many of you are in it right now? How many? Okay, that's that. So, the first place you see finite elements is called the direct stiffness method. Okay, direct stiffness is the precursor to finite elements. It's a very simplified type of finite element procedure where you can do some simple physics. Okay, now the problem here is when you move from that top line, so you're going through this design manufacturing process, and then if you want to do a simulation, you have to take whatever the current instantiation of the design is, and you have to like extract it, build a new model, and do a simulation on it. And then once you're done with the simulation, you have to take the results and then map them back into the CAD model. So like a good example is some of my friends at Ford, they say, you know, if I'm building a new prototype car and I want to do a crash simulation to determine its safety, you know, they call it passive safety. So they're the safety of the car in different types of crash scenarios. They're going through this design process. They take the model, and then to do the crash simulation takes about 15 weeks of time. So during that 15 weeks, they're doing simulation. What's happening to the design? It's evolving. It's still moving down the process, right? Because these are huge organizations. And so by the time they're done with the simulation, that particular model that they're simulating might be out of date with the current design. Okay, so there's this huge, massive, billion-dollar bottleneck in moving from CAD to simulation and back. What you would prefer would be that somehow you could just simulate directly on the design without having to kind of take it and then extract it from the process and do a separate set of procedures on it. Okay, but that is very difficult. Let me see if I can explain why. How much time do I have? Do I have till the end of the period? Okay. So let's talk about traditional engineering design. This is an inner hood of a Ford automobile. And this is what's called, this is a classic design built in a traditional CAD package. And the way that they build that is they take a whole bunch of little patches, we call them, and they stitch them together. It's all happening algorithmically under the hood. The designer doesn't even know that it's happening. But they're doing all these procedures in their CAD package, and underneath the hood is generating this really incoherent patchwork quilt of little surface pieces that are all kind of randomly put together. Okay, and it generates a huge mess. And so, for example, you may have gaps between the different patches. You may have overlaps, what are called sliver surfaces, where you have kind of like small intersections between patches that is not really physically relevant. And so this is sufficient to generate a picture, right? So the designer can look at it and you can say, oh, that looks like an inner hood. But simulation demands more than that, right? It's not just that it looks right. You actually have to be able to do something on it where you exercise its behavior, and that has to make sense. And so this traditional approach, generating this kind of like really dirty CAD, we call it, is the standard. And it's the genesis of the problem. So for example, here's a model from Honda. You probably could even see these in your own cars. These are called B-pillars. They run up between the front set of doors and the back set of doors. And there's a lot of interest in understanding and engineering those B-pillars because they carry loads in crash scenarios. And so a designer can build that. Doesn't that look beautiful? See, that's like a beautiful, smooth, exact looking piece of geometry. But let me show you what it really is. It's really the thing on the right. Okay, so what they've done is, like I said, they have this patchwork quilt of surfaces, and these algorithms are taking them and kind of putting them all together so that visually it looks good, but functionally and mathematically it's a mess. So all of those little things that are kind of spiraling off of the actual B-pillar are pieces of surface that have been cut away and not shown to the user. But they're actually there, and they need to be there in order to define the geometry. Okay? And so this kind of modeling paradigm is called BREPs, boundary representations. And so when we say, okay, now we want to run a simulation on this thing, we have to take this thing that when we render it on the screen, it looks beautiful, but we have to turn it into, like Mike was saying, a mathematical model, right? So the underlying description of the geometry has to be mathematically consistent in order to generate that mathematical model. And it's not. It's this piece of garbage here on the right. And this technology that underlies like all the big CAD packages, I mean, it's basically been static for over 3 decades. I mean, they've just kind of, they built these packages, they grew into massive companies, they have a monopoly on the market, and innovation has stopped in that domain. Okay. So, if you look at a simpler problem, let's say you have, this is a very classic example, this is one of the most important geometries in the history of graphics, right here. And does anybody know the name of this thing? Have you ever seen it in a Pixar movie? It is hidden in every single Pixar movie that's ever been made. Because there's 2 geometries that kind of as a joke, an inside joke, they put in every Pixar movie. It's this one, and there's a bunny. It's called the Stanford Bunny that they stick in. In your next Pixar movie, see if you can find this. You should want to find this because the name of it is the Utah Teapot. Okay? Because it's not an exaggeration to say that modern graphics was born in Utah. So it is pretty much dominated. If you look at all the major CAD and graphics companies, they have very strong Utah ties. So this is the Utah Teapot, and it shows what happens if you take 2 surfaces and try and stick them together using the traditional approach. What do? They take the body of the teapot, and then they take the spout, and the most simplest thing is let's just cram them together and define this intersection curve between the spout and the teapot. The problem is, that kind of seems like a good idea, but the problem is that mathematically you can't create an intersection curve that's watertight. And so every single time you do what's called a Boolean operation on a piece of CAD data, you generate cracks in the geometry. Okay? So it's not watertight, it doesn't hold water, so if you want to simulate with it, there's a problem because that mathematical description is not coherent. What you think is a watertight teapot is actually not watertight at all. Okay? And so when we want to move from design to simulation, we need to replace all this garbage with something that actually is coherent and makes sense. And this is why it takes so long to do it. So, who was I talking to? I was talking to, I don't remember now. It was one of the, it was either the Navy or one of the major automakers, and they were saying at this point in their process of building and manufacturing and designing things that are complicated, if you were to measure the total time to instantiate a design to manufacture it, the amount of time that they spend, so you have like the design process and then you have the simulation process. In the simulation process, can anybody, see if you can guess, what percentage of the total time do you think they spend just taking a CAD model and fixing it so that they can do a simulation on it? What do you think? Give me a guess. Is it up there? This is actually out of date. For most sophisticated things, it's greater than 90% of the total time is doing nothing but fixing it. So you take a design, you build it, it looks beautiful, and then if you want to run a simulation, you spend months and months and months just twiddling with nodes and cleaning up surfaces and trying to put a mesh on it. And 10% of the time, you actually are running the simulation. Okay? So like at Honda, for example, they have in their budget in their crash department. They spend about $8 million a year on Indian firms doing nothing but fixing dirty CAD geometry. Isn't that amazing? Okay. So, here's a better way to do it. What if we could come up with CAD descriptions that were always clean, that were always mathematically coherent, that at any point during the design process, you could run a simulation on it directly, without any cleanup, without any mesh generation, without any of these processes that are generating this huge bottleneck. And that is what I work in. It's called isogeometric design and analysis. And this is the new flow chart that you would see is you have your concept, and then once you instantiate the design, that design is built from a technology that is rich enough to be able to accommodate both what's happening in design and in simulation, and it completely eliminates all of that. And the consequences of this, I mean, there's a lot of details, obviously. I'm just kind of giving you like a 90,000-foot view. But the consequence is not only do you eliminate this bottleneck of going from a design into a simulation, but the design is far superior and the simulation results are far superior. So you get better results across the board. Okay? So in your education, you'll do probably more and more and more sophisticated designs. And at some point, many of you in your careers will probably be tasked with doing finite elements. I mean, most, if you're like, this is mostly a structural, I mean, I don't think water resources or geotech really uses finite elements, more of a, if you're in the structures area, I wouldn't surprise me at all if you ended up in firms where they're trying to get into this, because this is like where their next market is, right? If they can master this kind of capability, they'll be able to do a lot of new things that they won't be able to do. So you're going to learn a lot of traditional engineering disciplines, but you live in a world where what is traditional is becoming quickly irrelevant. Okay? So it's good to learn the traditions, and it's good to learn kind of the canonical examples. But as students, you should be smart enough to be looking forward and saying, what's next? Because the world is changing so quickly that what you learn today, in 10 years, there may not be anybody doing it anymore. Okay? And in the computational world that Dr. Borton and I live in, this is a rich new area where there's all kinds of new applications in the civil engineering domain for students that are interested in paying the price in learning what they need to learn in order to do it. So you should consider that as an opportunity. Thank you.